Welcome to homework.
Okay, we've got to draw a balanced chemical equation for the reduction of vanillin acetate, which has the formula C10H10O4 with sodium borohydride, which is sodium. Borohydride is BH4, that's minus, going to the high. So essentially what's going to happen is a hydrogen will transfer from the borohydride to the vanillin acetate, giving us C10H11O4 minus with sodium plus and neutral BH3. This can also be shown as follows, in which we include water, which will be protonating the vanillin, in which case it would be C10H10O4 plus sodium plus and BH4 minus plus water going to C10H12O4 neutral. That is, it gained one hydrogen from the sodium borohydride as well as just a single proton, positively charged proton from the water, leaving behind neutral BH3 again, as well as sodium plus, and because of the loss of proton from water, OH minus. This would be but either of these would be a valid balanced chemical reaction or chemical equation. Okay, now we're supposed to look at the structure of the starting material and products. So we've got starting material, vanillin acetate. And, oh, I made a mistake there. My mistake. Let me fix this really quickly. This is an ester. There we are. And this is vanillin acetate. Now, when this undergoes a reduction, this aldehyde will convert to an alcohol. That is NAB, H4. We will get, let's just make this ring in there. Okay, the ester is not touched, the ether linkage is not touched, but now this has become an alcohol. And we are left with Na+. Let's include the water here, plus OH minus, and our BH3 neutral. And maybe to hammer this home, we can put the charges here on the BH3 and the sodium plus. So how can we tell that a reduction took place? Or that there was an oxidation reduction reaction? Well, for one, this carbon has been reduced. The oxidation state of it before was higher because it had two bonds to oxygen, whereas now it has a single bond to oxygen. So that's indicative of a reduction. The other hint we have that an oxidation reduction took place is if we look at our borohydride turning into BH3. It's lost its charge. It's become oxidized. It was BH3 minus, and under oxidation, or BH4 minus, and it was oxidized, losing a bond to hydrogen. to become neutral BH3. So those are two clues that we've seen in oxidation reduction reaction. Now, finally, we've got to see a arrow pushing mechanism for this reduction. So we will start again with our vanillin acetate. Hydrogen. Recall again that sodium borohydride is only a strong enough reducer to reduce aldehydes and not esters, for example. So this part of the molecule will not be touched because it's an ester. Esters are more stable and won't undergo reduction with relatively weak reducing agents such as sodium borohydride. Luckily, this mechanism isn't too complex. We start with BH3. It's actually BH4. We'll show that extra fourth hydrogen right there and the negative charge. Now, this bond gets broken to attack the carbonyl carbon, and the double bond will hop up onto the oxygen. So it's actually the migration of this entire unit. It's not going to be just the proton moving, it's the proton and its electrons. So our product, quickly draw this skeletal structure. So apologies for how messy it is, but it's fairly unimportant to the rest of the problem. Okay. Now we're left with O minus, where we used to have a neutral oxygen. This hydrogen is still here, but now we have a new hydrogen. In fact, if it helps, I will highlight this in blue to show where this hydrogen came from. Those are the same hydrogens. Finally, it's typical to show a final step in which water is introduced. Sometimes this will be sulfuric acid as well. The important point is that there's a proton transfer step to protonate the alkoxide. So you go from a charged oxygen to an uncharged species, giving you your final product, which you've seen before, but let's draw it one more time. Ester, methoxy, and now simply an alcohol. Side products, well, we've got our BH3. Theoretically, we've always had sodium floating around, so we could go back to the beginning and draw this in at each step that, there's a sodium here just floating around, and there's a sodium here just floating around. It's not entirely necessary, but some professors want you to show all ions in all steps. And additionally, we introduced water, which is deprotonated, so now we have OH minus, which would theoretically associate with the sodium to form sodium hydroxide. If this were in an inorganic solvent, in fact, this might actually precipitate out as a salt. But in water, it would be fully ionized. Given that the last step included adding water, this is likely taking place in water. There we are.